Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Kalina from Business Review, and I will be your host today. It is our pleasure to have QPS with us today, who will be presenting this webinar titled Human Radiolabeled Mass Balance Studies for Regulatory Submission. Today's guest speakers are Fred Van Hulen, Director of Elemental Analysis, and Diane Grotz, Biotransformation Group Leader. I would like to welcome you to our webinar platform on 24. You will notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top corner of your screen and click Submit. Towards the end of this session, we will allocate some time to address any questions or thoughts that you may have. Please also use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Fred Van Hulen. Fred, over to you.
Yes, hello, also welcome from me. In the next 20 minutes, I will tell you something about human mass balance studies and more from a practical and general point of view. In the next slide, you will see the key learning objectives for this talk. The first is the typical analytical aspects of a formulation analysis in relation to the mass balance study. And the second, the analysis of human study samples to determine the recovery of a radioactive labeled drug in a mass balance study. For the first, we will have a short look at what radioactivity is, the workflow for this kind of studies, the acquisition and the CMC part, and the validation. That is all for the formulation part, and then after dosing, what will be done is the first item, the second, the measurement of total radioactivity, then something about the matrices and sample processing, and of course at the end, data processing. The next is the key learning objective for the talk after my talk, so I will skip this. And then we go to the first part of my talk, the formulation analysis. Radioactivity, should we be afraid of it? No, of course not, otherwise we won't do this kind of studies, but it's, I think, very good to have a little better look at it, because we need to know what exactly we are doing if we are working with radioactivity. And part of my job is also that I'm the local radiation expert for this kind of studies. That means that I'm also responsible for good radiation hygiene and safety during the study. And it's good to realize that it is not only the radioactivity in a particular study that counts, but the radioactivity is a cumulative process. Thus that means that the summation of all received doses in our life counts. And it is a stochastic effect. That means that even a low dose has a chance to develop a so-called late radiation effect. For that reason, many years ago, the ALARA principle was defined, which means that for the activity, we should always aim for as low as reasonably achievable. That means that we always calculate the radio burden, that means the effective dose that people receive during these studies. And it is also illustrative when we have calculated that dose just to compare it with, for instance, a background radiation dose or other situations, for instance, an international flight, in order to have some idea what kind of radioactive dose the volunteers will receive. Now, just two small examples. For a first mass balance study, we have dosed volunteers with pacritinib, a 14C study, where the volunteers were given a dose of 100 microcurie, and that corresponds to an effective dose of 0.8 millisievert. Just for you to have some idea, the yearly background in the Netherlands is about 2.4 millisievert. This means that for such a study, you have about 1/3 of yearly dose as an extra dose upon what you already receive. And as it is cumulative, that means that at the age of 60 years, you have about an increase of 0.5%. For a typical microdosing study, we usually dose about 1 microcurie. And that means that the effective dose is about 20 to 21 microsievert. And just for some idea, this corresponds to 3 days background or 2 X-ray images at the dentist. So you can see that the dose is low, but still it is important to work with as good as possible, and just to realize that it is always counting up in for every study, and always from a contamination point of view, it is good to realize that for a mass balance study where the dose is much higher, by contamination and combined with the high half-life of 14C of 5,700 years, you can build up such a contamination that you cannot do even any microdosing study anymore, because the dose is there so much lower. So let's go to the next slide. The workflow. Just to have an idea how things are logistically done from the beginning to the end through the whole mass balance study. Of course, everything starts with having a good radiolabeled compound. I have this given another color because this is something which is not done at QPS, but it's good to realize that this is very important because it can take quite some time. I have given here 10 to 12 weeks. That's an average. 6 to 8 weeks are very fast. It means actually that there is already some knowledge, for instance, from a preclinical study. But if you should start from the beginning and it is a complex label situation, then it can take even half a year or even longer. So it's always good to realize that this should be organized in the beginning of the study and should be done well prepared. The next part is the acquisition phase. Also, this is very important, and you can see there are a lot of items which are described here, and all these items means that the knowledge should be there already in the beginning in order to have a successful start of the study, but also to have an idea of a realistic cost situation for these kind of studies. In the next sheet, I will go into a little bit more detail for some of these items. Then, if everything has been started in the acquisition phase and we have a proposal and we can start, there is a contract, well, then, of course, we need to have a method transfer and a validation. If the method has been validated, we are ready for a mock. This is some kind of a general repetition, a rehearsal, in order to verify if everything is going well and well prepared for the final dosing. And if we conclude that that is done and the mock has been successfully completed, we are ready for the final dosing for the study. And that means from the beginning of the acquisition phase to the GMP final dosing, we are usually taking about 3 to 6 months. Let's have a look at some of the items in the acquisition phase. During the acquisition phase, we need relevant information in order to determine feasible and realistic timelines and costs. And for instance, I have picked out some of the items which can influence the situation much. For instance, if there is a suspension instead of a clear solution, when the IV dosing, or if there is an IV dosing instead of an oral, if there is a situation that we have an oral solution, but it turned out that there is a bad solubility of the compound, when there is no good validation or validated method available for the Hplc to characterize the formulation, when there is no stability data available or compatibility for the oral and IV dosing container material. I have just mentioned these things because they all turned up during some of the studies in the past at QPS, and usually depending on the item, but this can have a delay from several days to even 2 months, in particular if the labeling is, for instance, not done well, or there is stability item which is lacking. The provider of the hard material is also important to have that already in the beginning, because we need the address and contact details for arranging the import license. We need to have knowledge about the ratio between hot and cold, at least if there is a mixture given of hot and cold, of course, but also the specific activity in microcurie per gram or microcurie per mil is very important. Then, of course, we need to know what is the activity that should be dosed. Is it a microdosing or a human mass balance study? The microdosing usually is between half a microcurie to 2 microcurie, and the mass balance studies are usually between 50 and 100 microcurie. And this determines whether a dosimetry report is required. A dosimetry report, in a dosimetry report, the radiation burden is calculated, and this is this is needed and required to get the approval from the medical ethical committee. If there is no dosimetry report available, QPS can arrange that. The validation. Typical validation design is done by Hplc UV, always done by using the cold compound, and the parameters that are done are sensitivity, repeatability and accuracy, identity, linearity and carryover. Depending on the design or the compounds, it could be that there be some more items. Deliverables are a protocol, Excel files and reports. When the hot compound is received, this will be characterized by identity, content, and purity or impurity, and also the activity. And there's always a requirement for the activity. This should be within 10% of the value provided by the manufacturer. When the hot compound is characterized well and the activity corresponds with the right value, we can prepare a mock test. Usually within the mock test also a stability period is included, usually 24 or 72 hours or 2 time points. And we can then do the mock test and determine whether we are ready for dosing. For the mock samples, we prepare the exact dosing samples that will also be used for the final study. And that means that also the same characterization will be done already during the mock. And this includes the identity, content, chemical, radiochemical purity, and the activity. The deliverables are usually a certificate of analysis and Excel files, including all the data. And of course, when the mock test has been completed successfully, we are ready for dosing, and dosing will be done in the same way as that was done using the mock, but here the dosing will also be released by the qualified person, because this is all done under GMP conditions. Okay, now we have the formulation ready. We have done the mock and we are ready for dosing. So in the next part, we will have a short look what will be done after dosing. Usually we have 6 to 8 male volunteers on day 1. From day 1 on, several samples will be collected, whole blood samples from day 1 to day X. Day X is the final in-clinic day. And from all the whole blood samples, also plasma samples will be prepared. From the same day, also urine and feces samples will be collected in different time windows. These are required for determination of the recovery. In special cases, we can also collect expired air samples. From the day one to from day one on, we measure all the samples as a way that we call quick counts. That means that we limit the sample counting time to 2 minutes per sample, and that during this time we focus only on the discharge criteria. This means that we will look if the recovery is 90% or larger than the dose that has been provided to the volunteers, or that we have two successive time points where the final recovery is below 1% of the dose. When these criteria are met, the volunteers can leave the clinic. If that is the case, then from that moment on, all samples are recounted, but done with a more accurate counting protocol, and that means that all samples are at least counted for 5 minutes, and this is depending on the amount of radioactivity in the sample. Some about the matrices and sample processing. The radioactivity in the beta counter is measured indirectly. That means the beta counter doesn't measure any radioactivity, but it measures light. The electrons that are emitted by the beta 14C element react with the liquid scintillator in the solution, and then the photons that are produced are measured in the beta counter. Well, that has a direct consequence because the light is measured. The samples need to be clear in order to measure all photons that are produced. That means that whole blood samples and other samples which are not clear should be pre-treated in order to count them accurately. In this case, the whole blood is burned in an oxidizer. That means that everything is burned, and the CO2 that is then trapped on the column is then washed from the column and collected in a liquid scintillator cocktail, and it can then be directly counted in the beta counter. Feces samples, 24-hour stool samples are collected. They are mixed one-to-one with water. Sometimes there are some additions, but usually only with water. They are homogenized using a Turax. And then from the homogenate, we take samples of about 250 milligram. These are brought in some small paper cone and are burned in the oxidizer using the same procedure as whole blood. So in both cases, whole blood and feces, we end up with a clear sample which can be directly counted in the beta counter. Plasma samples and urine samples are clear enough from themselves, and they do not need a special pre-treatment. So they are just diluted with the scintillation cocktail. For the plasma, we usually have a sample volume of 250 microliter, and the urine samples are typically 1 ml. All samples are measured in duplicate with the criterion of 20% on C. Just a picture here how it happens. At the left side, we see the plasma and urine samples. The urine samples are collected in large containers of maximum 3 liter. And these samples need to be very good homogenized. Then we prepare different samples, usually 3 samples, 3 aliquots of 35 ml. One will be used for counting purposes, and the others are stored for backup or metabolite profiling and can be sent to other labs. For the plasma, we have small containers of maximum of 2 ml, which are usually filled with about 0.2 ml of plasma. The whole blood, the same. Also small vials, and the feces samples. At the top, you see that oxidizer picture, which is used for the whole blood and the feces samples. You see also right at the right side the thorax bar. The homogenate is then stored in buckets of 1 to 3 liter, and then after homogenizing, we prepare aliquots also here of 50 ml and 3 usually for the same purposes as the urine samples. At the low side, you see the beta counter, where the samples are counted. The beta counter will be calibrated every day, and we always include QC samples, quality control samples with the known activity in order to be sure that the activity that is measured is correct. When we have measured the samples, we end up with a lot of data. Here you can see an example of plasma data. At the left side, you see the volumes, then the different time points, and at the most right side, you see the nanogram equivalent concentration that can be calculated from the amount of becquerels or DPMs that are measured. So we measure the radioactivity, but we can, of course, recalculate that to nanogram equivalent of the compound, because we know the mole mass of the compound and we know how much we have dosed to the volunteer. And you can see at the low side of the picture, the samples become, after day 2, all lower than the LLOQ, the lower limit of quantitation. And if you have 2 successive samples which are lower than the LLOQ, we actually are at the point where we can stop. And means that for this typical example, at day 3, day 3, the volunteer has met the criteria for the plasma. Well, the same is done for feces and urine. Here we have given an example of a table for the feces. At the left side, you see the time points, then the feces weight, the added amount of water. That means that you can calculate the total amount of the homogenate, then the number of DPMs, the disintegrations per minute are given, which are counted by the beta counter. We can recalculate that if we have the aliquot weight to the amount of megabecquerels per gram. That means that at the 2 right sides, these are the most important. We measure the percent recovery on a daily base. And you can see we start, of course, with 0 for the pre-dose, then 0.04 day 1. Then you see the recovery is increasing suddenly to 14%. The next day also 40%. Then it decreases 4.5, 0.3, 0.1, 0.02, and then 0. And so that means also here you can see at day 6 we have 2 successive time points where the excretion is below 1% of the dose. And at the most right side, all the daily excretions are, the daily recoveries are summed, and you have the cumulative recovery. And you can see that you end up with 33.5% recovery of the dose that is obtained here in the feces. The key takeaways that we have for this part of the study, human mass balance studies and microdosing studies are logistically challenging studies, and they should therefore be well prepared. In particular, for the CMC part, there are many items that can determine the success in the timelines. Means that we need a close cooperation between sponsor, lab, and pharmacy. The bioanalytical part of the human mass balance and microdosing studies, the determination of the total radioactivity is routinely done, but the challenge here is also the logistic part more than the science. And that's also because we have many samples, feces, plasma, urine, maybe expired air, whole blood, and they all need to be counted in, first prepared and counted in a very short time. This is my part. Thank you for your attention. And then Diane will go to us for the next part.
Yeah, so hi, I'm Diane, and I would like to talk to you about the metabolite profiling part of the study for a human hAME study. And the first thing I want to mention is the objective of this part of the study is to understand the full clearance mechanisms of the drug and its metabolites. So I think, as Fred mentioned, we do typically a single dose at the intended route of administration. So if your drug is intended to be an oral drug, then we do an oral dose. We use C14 almost exclusively, and part of the reason for that is that 14C is much more stable. With tritium, you have to worry about tritiated water loss, and you don't have to worry about that with 14C. However, the position of the radiolabel is important because of metabolic liabilities. So if your compound has an ether linker somewhere in it and your radiolabel is on one side or the other of that linker, you may actually have your compound may be prone to O-dealkylation, in which case you may lose part of that molecule. And depending on where the radiolabel is, the cold side of that molecule will no longer be able to be, we won't be able to assess the levels of those metabolites. So what we do is we measure concentrations of parent and metabolites and determine the amount of radioactivity in the plasma, the urine, and the feces. And what we gain from that is the primary mechanisms of elimination and excretion from the body. The circulating metabolites are very important. So this is also known as systemic exposure and/or percent of drug-related material. And what you can do at the end of these studies is compare to the preclinical metabolite studies and see whether you have coverage of the various pathways observed in human by the tox species. So this is a brief metabolite profiling timeline, and this timeline, by the way, assumes that everything goes well. Not everything goes well, so this is hopefully what you will get, but it isn't always the case. So our timeline starts at day 0, which is when we get the QA mass balance data from the clinical study. And then what we do is we take those data and we create an analysis scheme that takes 1 to 2 days. And then after that, we start pooling the samples. Those samples come in at -70 degrees. And so they take a while to thaw. This is not like your refrigerator at home. And so that's 3 to 5 days, depending. And then we do radioactivity recovery in the various matrices. That really takes a minimum of 2 weeks. We need to do various things. A lot of this I will be going into later on in the presentation. We also do sample stability, and that goes on through the study. So we started in the beginning to make sure that we know what the radio profile looks like, and we continue to do stability as we go on. Then we do the Lcms method development. That can take 10 to 15 days for separation, and then we go to metabolite profiling. This is a lot of where the time is hopefully concentrated, and this is 3 to 5 weeks for identification and structural elucidation. Then we do the radio quantitation and the AUC samples. That's generally 1 to 2 weeks. Those happen after the profiling, so hopefully everything looks exactly the same in the radio quantitation as it did in the profiling samples. And then we go to the report writing, which takes 2 to 3 weeks. The reason it takes 2 to 3 weeks is that these are long, complicated reports, and we want to make sure that you have all the data that you need to go to the regulatory agencies. So that report that you get is a draft report, and once it's finalized, approved by the sponsor, and everybody's happy with it, then that report will go into the clinical study report. So it's really safe to assume that you're going to have a minimum of 4 months from the time the QA'd mass balance data arrives before the draft report is ready. So now I'd like to talk about the study itself. So once we get the mass balance data, we look at the radioactivity recovery in the excreta and the amount of radioactivity in the plasma samples. And one of the things that you should look for is the excretory pathway of radioactivity, because that can give insight into future human studies. So if 99% of your radioactivity comes out in the urine, then you may want to include in the future a special renal impairment group. There's also, we do the pooling schemes are based on the amount of radioactivity in the different matrices. And there are 3 types of samples. There's profiling samples, radio quantitation samples, and the radio quantitation AUC pooled plasma samples. So the profiling samples are pooled across subjects and time point, and there's 1 sample per matrix. The radio quantitation samples are pooled across subjects at each time point or time interval. And for those types, we have urine, feces, and plasma. And for the radio quantitation sample, the amount of radioactivity determines the number of samples that we're going to analyze. The AUC pooled samples give a single sample for each subject. So basically what that looks like is you get a radio trace that would be similar to a combined PK study. So it shows in proportion, it shows the metabolites and the parent as it would look if you did it over time. One of the things that you get from an AUC pooled sample is the potential to highlight unexpected phenotypic differences. So, for example, cytochrome P450-2D6 is known to be variable in populations, and approximately 7 to 10% of Caucasians have very little. There's also a number of people who have a lot of it. And so if you have a compound that's metabolized by CYP2D6, then you may have to worry about drug-drug interactions, because a low metabolizer will have more of your compound in plasma, and an ultra-rapid metabolizer will have less. The sample pooling, we do the profiling samples first, and as I said, you get 1 representative sample per matrix, and each of those samples should contain 85% or better of the radioactivity in that matrix, because we really want it to be a representative sample of the entire study. The urine and fecal samples are pooled in proportion to the sample volume or weight. The plasma samples are pooled using equal volume aliquots. The profiling samples are really where the bulk of the work comes in. So those are used for radioactivity recovery assessments, the method development on Lcms, and the metabolite profiling and the structural elucidation. Those are all done on the profiling samples. We start with urine, partly because there's a lot of it, partly because it's an easier matrix to start with. Then we move to the feces, and plasma is last. And the reason we do plasma last is because there's limited volume. And the plasma is profiled on our most sensitive instrument, which is a top count static radio detector. And the reason for that is that there's low radioactivity. Radio quantitation samples are pooled across subjects at each time point. And like I said, so it's based on how much radioactivity is in each sample. So if you have no radioactivity observed in, say, the 96-hour feces, those samples won't be pooled for radio quantitation analysis. The AUC pooled samples will be prepared and reported for each subject, and those are run pretty much last. So after everything else is done and we're positive we know what's going on, then we run the AUC pooled samples. We also do recovery of radioactivity and look at sample stability, so the samples are stored at -70 until analysis. We may analyze them once and then put them back in the freezer. So we look at sample stability, and we look at processing time. So 3 to 4 hours on the bench, freeze thaw. Does the sample look the same after we put it back in the freezer and then took it back out? We look at stability overnight in the autosampler, and what we're looking for is not just the stability of the parent, which sponsors usually know at this point, but what we're looking for is stability of the entire radio profile to make sure that the metabolites are also stable during these processes. The recovery of the radioactivity is evaluated for each matrix, and what we do is a representative sample. So we don't do radioactivity recovery on every sample. We do the radioactivity recovery on the profiling samples, which have the 85% or better of the radioactivity in each matrix. And the reason we do the radioactivity recovery is to ensure that the profile that we're reporting is really representative of the actual samples. Urine samples are analyzed directly after centrifugation. That's usually the easiest, and we need 90% or better of the recovery. Then that's usually very simple for centrifugation. If necessary, we can concentrate them down and reconstitute them. We try not to do that because there is the possibility for the samples to change. Plasma and fecal samples are extracted with organic solvents, and the targeted radioactivity recovery for the extraction part is 85% or better. And if we don't reach 85% or better on the first extraction, we will try again. If we still don't get it, we may need to try different solvents. And once we've reached 85% or better, then we can go to the sample dry down and reconstitution step. And we need, for that part of it, we need 90% or better. And all those recovery and reconstitution, and for the urine, all of those are done in duplicate. So on the right, what you will see is a typical radiochромatogram. And right now, what I'd like to talk about is our LCMS radio detection system. So we use a Shimadzu Nexera Hplc. For small molecules, we have a SciEx triple TOF 6600, which is a high-res mass spec. And for the oligonucleotides, we use a 5600. We do electrospray ionization, either positive or negative, depending on your compound, also depending on the metabolites that are formed. And the accuracy of these systems, as long as the peaks are fairly decent, is within plus or minus 5 ppm. That's parts per million. So the radio flow detector that we use for profiling of excreta is a LabLogic Beta RAM, which is where this radio trace came from, that system. And 90% of the column flow goes to the radio flow detector and 10% goes to the mass spec. And the reason we can send just 10% of the mass spec is because we're doing electrospray and you don't need a lot into the mass spec to get a good signal. So the fraction collection that we do for radio quantitation samples happens offline. We collect fractions, we dry them down, and then we count them on the top count. So plasma is always done on the top count. Urine and feces, it depends on the radioactivity. And the top count has much better sensitivity, which improves your accuracy as well compared to the radio flow detector. And what we do is we integrate the peaks. So in the radio trace on your right, what you'll see is peaks labeled M1, M2, M3, M4, and parent. And we integrate the peaks to calculate the percent of radioactivity in each component in the matrices. So for the method development, what we really want to do is separate each peak so that we can determine percent of radioactivity attributable to individual components. So what this means is in a non-labeled study, you can have some coelution, but for these kinds of studies, especially in human, we really want as much as possible to be able to attribute each radio peak to a particular component. So what that means is the analytical runs are practically always greater than 20 minutes, and we've had lots of them that are 30 minutes and longer. The radioactivity recovery from the Hplc column is also assessed, and that's also done in duplicate. And what we do with that is we collect 2 injections made without the column and 2 injections made on the column. We collect those samples, and then, as Fred described earlier, we put them on a liquid scintillation counter, and we need to get 90% or better on the recovery. We use electrospray ionization for the development of the method, and the method is agreed to by the sponsor. And as I said before, we could use positive and negative. Both will be evaluated, and we may need to use both. The fraction collection part, if we need to do method development using the top count, using fraction collection, that extends the timeline significantly. The radio flow detection, basically you inject, you can watch the radio trace come off. With fraction collection, you have to dry down the samples and then put them on the top count. That's a minimum of 6 hours from the time that you start the samples to the time that you actually see the radio trace. So any method development, any changes in the gradient, any changes in the mobile phase, anything like that can take quite a while. So now I'd like to talk about the actual metabolite profiling part. And the instrument that you see to the right is actually a SciEx 5600. The SciEx 6600 looks just like it, except it's a slightly different shade of blue. So our target is to get 5% or better of the radioactivity in each matrix identified. So the reality is that if we will identify everything we can, if we can identify things that are 1% or less, we will do it. The expected metabolic pathways are definitely one of the things that we look for. And also if you have previously reported metabolites, we do targeted MS-MS, we interpret the product ion spectra, then we propose metabolites and with their structures, and we also do a metabolic pathway proposal. Any authentic reference standards that you have, so we will definitely have one for the parent. You may have some for the metabolites based on preclinical studies, and we will look at those for retention time and fragmentation to match with any metabolites that are observed in human. We use vendor-supplied software to aid the search for unknown metabolites. Since we use SciEx instruments, we have PeakView and Metabolite Pilot software. And some of the things that those pieces of software are good for is that they can do predictive fragmentation for compounds that we are having a hard time with. Isotope pattern filtering, precursor ion and neutral loss filtering as well can be useful. And the high-res mass specs, basically the really useful thing about a high-res mass spec is you get accurate mass. So you can use that to confirm the molecular composition and the proposed structure. So the accurate mass is not just on the intact component, but it's also on the fragment, which helps with the structural elucidation. And next, I would actually like to talk about the structural elucidation. So like I said, you look at the parent and any authentic standards, retention time and fragmentation. All of that is used for structural elucidation of unknown metabolites. And what we get with the accurate mass confirms the structures and the molecular composition. So to the left on the bottom, what you see is an example of a verapamil and fragmentation that you may get from verapamil. And what you'll see is that there's one fragment to the right side, and then there are 3 fragments to the left side. That's what those little dotted lines with the arrows mean. And so one fragment on the left is after that central nitrogen in the middle of verapamil, and 2 of the left-hand fragments are before that central nitrogen, and the right side excludes that central nitrogen. So what that does is when you get metabolites for verapamil, you can then decide which side of the molecule is being metabolized. So norverapamil, if you look to the right on the metabolic scheme, norverapamil is one of the major metabolites for verapamil. And as you can see, it's lost the central methyl group from the central nitrogen. And the reason that you can tell it's that particular nitrogen that's been affected is that the right-hand fragment is probably unchanged, the far left fragment is probably unchanged, and those 2 central left fragments have either disappeared or they've changed and they've lost 14 Daltons, which is indicative of loss of CH2. And the metabolic scheme that you see to the right is kind of a simplified metabolic scheme for verapamil, and it shows that you can have N-demethylation, N-dealkylation, O-demethylation, and then you can have combinations thereof. So that's the kind of thing that you would get in your reports. And but one of the things that I want to stress is that the hardware and the software are great, but what you really need is somebody who knows what they're doing. And for our biotransformation group, we have 3 PhD level scientists, and we average 16 plus years of experience. I'm in the plus section. And then we have 10 to 12, QPS itself has been doing 10 to 12 regulatory studies per year since 2002. And then we talk about the radio quantitation. The plasma, urine, and fecal samples are, after they've been profiled, then we do the quantitative profiling. So each radioactive peak is identified, integrated, and compared to the amount of radioactivity in that matrix. Urine and fecal samples are reported as % of total dose administered to the subject. And depending on the amount of radioactivity, we will either do that on the radial flow detector or we will fraction collect and do that on the top count. The plasma, like I said, is always done on the top count because of the amount of radioactivity that's observed in plasma. And the concentration of each radioactive component observed in plasma is reported as nanogram equivalents or microgram equivalents per mil or gram. The HPLC, it's always fraction collected because of the low radioactivity. The individual components are then analyzed using Win-non-Len to get a total AUC, and that will show you the percent of AUC for each component. And after all of that is done, then we do the AUC pooled plasma, and those samples are analyzed for each subject, and you can see if there's any inter-subject variability. And of course, what you want is that there isn't. So the reported data that we give out, this is the first time that you're going to see a full metabolic pathway in human. And the important parts, of course, are the systemic exposure. Are there any circulating metabolites, 10% of the drug-related material or higher? So on your right, there are two tables. The top table is urine, and on the left, what you see is the components, so metabolites 1 through 4, and then parent at the bottom. And you get, over time, you see the amount of dose excreted in urine for each component, and then the total is shown to the right. For the plasma, you have basically the same type of table, except for this, it's nanogram equivalent or microgram equivalent per mil in this case. And for M1, that it's shown as below the limit of quantitation. And what that means is that either on the radio detector, we didn't get a significantly sufficient signal, so 3 times signal to noise, to be able to integrate it appropriately, or there was no radio signal at all, which might happen if you've lost the radio label for that particular metabolite. And for M2 and M3, the percent of AUC, if you go to the far right column, the percent of AUC for both of those metabolites is very high. And so those metabolites would need to be monitored going forward in any clinical samples, in any clinical studies. The reports that we give out are suitable for regulatory filing. You get proposed metabolites with the fragmentation and structural elucidation. You also get the proposed metabolic pathway. And the parent and metabolites reported are as percent of dose in urine and feces and as microgram equivalents per mil or gram in plasma as percent of AUC. So the metabolic profiling key takeaways for this particular section are that the excretion pathways of parent and metabolites may provide information on future clinical studies. Do you need to look at drug-drug interaction studies? If you have a CYP2D6 compound, you may. Or do you want to look at special inclusion groups such as renally impaired people? Then there's the circulating metabolites. Are your metabolites approaching or exceeding to 10% of the drug-related material? And can you compare those metabolites that are observed in human to the preclinical ADME studies? Do you have any human-specific? You may need to do a few further tox studies. Reported data includes the proposed metabolites with elucidation and pathway, the excreted parent and metabolites as percent of total dose administered, and the circulating parent and metabolites as percent of AUC, also known as systemic exposure. And it also includes the comparison of the AUCs across subjects. And at that point, Fred and I would like to thank you very much and for your attention, and we will now turn it over to Kalina for questions.
Thank you very much, Fred and Diane, for this presentation. Indeed, it is now time for our Q&A session. Just a reminder for the audience that in order to send in questions, you can do so via the questions widget at the top right corner of your screen. But it looks like we've got some questions coming through already. So the first one for today is, can QPS develop formulations to be used in an hAME study?
Could you repeat the question, Kalina?
Yes, certainly. The question is, can QPS develop formulations to be used in an hAME study?
Whether we can do all kind of formulations, is that a question?
Yes, whether you can develop formulations to be used in human radiolabeled mass balance study.
Yeah. No, QPS does not develop the formulation itself. That is, quite specialistic. But we characterize the formulations. We can, of course, assist to a certain extent in developing formulations, but it is not within the core of QPS that we develop formulations.
Thank you very much. The next question that we have is, what kind of stability data can QPS provide?
The stability data within my part for the formulations is usually limited to the time that is covered between the preparation of the dosing solutions and the dosing itself. And that is usually 48 or 72 hours.
Thank you very much. The next question that we have is, compatibility standard included in the formulation characterization?
No, this is not standard. In principle, QPS assumes that there has already been done some compatibility work at the sponsor, but in exceptional situations, we can certainly do this, and usually this is done in close agreement with the sponsor.
Thank you. Another question that we have is that GMP required for microtracer study? Sorry.
Yes, in principle, GMP is required unless the API percentage is below 0.15%. In that case, the compound may be considered as an impurity because of the guidelines. Usually this is only the case at microdose and microtracer studies because the concentration here is usually very low. In that case, the radioactivity is more important than the content of the compound itself.
Thank you very much. This is all the time that we'll have for questions in today's session. So just a reminder for the audience that if your question did not get answered today, it will be available to be answered at a later date. So that just leaves me to thank Fred and Diane for this presentation and to QPS for sponsoring this session. To the attendees, you will receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned and follow us on Twitter at BR Webinars for daily updates. You can also join our LinkedIn group, Business Review Webinars. Thank you all once again, and I hope that you have a great day.